All right, so finishing up our series of lectures here on modeling crown fire initiation and spread. All right, so far we've seen our equations for predicting whether or not initiation can occur, and then the previous lecture we were talking about sort of the criteria for minimum spread rates and bulk densities at which crown fire spread would be possible. And so now the final step here is to actually make a prediction about the the final rate of spread once an active crown fire occurs. Right, so we saw, right, Van Wagner 77 gives us this equation that predicts the critical spread rate necessary to sustain a crown fire under a given canopy bulk density. Right, but so now we're kind of wondering, well, how are we going to predict a crown fire is going to occur if we already need to know the rate of the crown fire's spread to do that? So we're going to need to independently estimate the rate of spread um, were a crown fire to occur in a particular stand, and then we can compare that predicted rate of spread to Van Wagner's critical rate of spread, and that'll give us our prediction of whether or not active crown fire is going to occur. So to do this, we're going to need yet another model to link to this Van Wagner 77 paper. And this model is going to actually come back from the same guy whose research went into developing our surface fire model. We're gonna pull from this paper from Rothermel 1991, where his main goal was to develop an empirical model to predict crown fire rate of spread. In this work, he's only talking about crown fires where the behavior is being driven by wind rather than a plume-dominated fire. Plume-dominated fires being when we have so much heat release rate coming from the fire that the whole atmosphere and the whole local winds are really driven by the fire, and that really changes the dynamics versus the fire being pushed by more the actual ambient wind flow. Um, so we're only talking about the wind-driven types of crown fires. And so he pulled data from these 8 wind-dominated crown fires in the northern Rockies, and basically just builds a statistical correlation to predict rate of spread. So the fires he selected all had a variety of information about them, right? They all have a name, but they had some measurements of the surface fuel moistures, the wind speeds at 20 feet, right? That's our 20-foot open wind speed, so either 20 feet above bare ground or 20 feet up above the canopy. They had some estimates of slope, the elapsed time and distance of spread, right? So that gives us an average rate of spread within that time of crown fire, as well as maybe the maximum spread rate that was achieved during the period of interest. So here's his table of the 8 fires that he ended up using to build this model, and the associated data that was available on them. So basically, what Rothermel did is he first made an estimate of the surface fire rate of spread using his 72 equations for fuel model 10, which is our pine and pine understory fuel model from the original 13 fuel models. He used a wind reduction of 0.4 and all the environmental variables, right, that were collected around each of those fires, and basically tried to relate the surface fire spread for fuel model 10 to the actual observed rates of spread for the active crown fires. Okay, so in this table here we see the fire really the fire behavior measurements, or the rate of spread measurements that were made on these fires, as well as some of the model calculations. So the first thing to see here, right, is we've got the distance and time. So how far did those fires spread over certain time periods? And then the big R there is basically just the average rate of spread throughout that time period. R max was the max measured or observed rate of spread, and then R10 is actually the predicted rate of spread, surface fire rate of spread for fuel model 10. Right, that's what that subscript 10 is representing. And then moving over, we have basically the ratio between the observed average rate of spread and the rate of spread for fuel model 10, and then finally the ratio between the max rate of spread and the observed rate of spread. So just basically how, based on the measurements they had, how variable was the rate of spread during those time periods. But the real important here is the ratio between the rate of spread and then that modeled surface fire rate of spread. Because really what that number is saying, that for the Sundance fire in that first burn period, that the active crown fire was burning a little more than 3 times faster than what would have been predicted if it were a surface fire. That second later burn period, even faster. It was almost 4 times faster than the prediction for a surface fire under fuel model 10. And then, as we'll see, Rothermel is basically going to use this ratio to build us a simple equation to predict our crown fire rate of spread. So here's what those fires look like plotted out. Right, we're on the bottom axis there is the predicted surface fire rate of spread under fuel model 10. Once again, inputting in all the other environmental variables we had for all the different fires. Right, on our y-axis is the actually observed active crown fire rates of spread. And we can see those points actually plot out on a fairly reasonable kind of linear relationship there. And basically he found that the mean ratio between the predicted surface fire rate of spread and the observed crown fire was about 3.34, right? So the crown fire tended to be about 3.34 times faster than the prediction for fuel model 10's surface fire. And you can see that basically gives us this pretty straightforward equation to predict active crown fire spread. Right? Simply all we need to do is input in all our environmental variables, run surface fire prediction for fuel model 10, and then whatever rate of spread we get out, we can just multiply it by 3.34, and there's our active rate of spread under Rothermel 91. So once again, it's pretty simple empirical correlation here. No attempt to solve any heat transfer equations, at least related to the crown fire. Right, we're doing all the same heat transfer stuff that happens in Rothermel 72 for the surface fire, but the crown fire is just getting represented by that multiplying factor there. So this pretty simple approach was really designed as just like a first approximation of crown fire rate of spread, and it's fairly limited in that it can only really apply to fires where right, the ambient wind is really driving the behavior. And Rothermel also points out in his paper, right, that any given crown fire, throughout a run, which is just some period of time where there's a lot of crown fire activity and maybe some somewhat consistent behavior, but even within a given run, a fire might switch back and forth from being plume dominated and wind dominated behavior. There's no consideration of the canopy fuels in this rate of spread, right? The bulk density or foliar moisture, or maybe spatial heterogeneity within the stand, or within multiple stands, we might be predicting this across. And then, as we've seen, right, all these sort of empirical relationships we're looking at are really dependent on the data you have or the data you use, and so in this case, our equation here is limited to these measurements made on just 8 fires in the Northern Rockies. So since he put out this correlation, there have been a couple of attempts to extend or just build on a couple more features onto the equation. So one of these is to make an adjustment for foliar moisture content. Right, the moister the crown needles, the more energy they're going to need to ignite. So that would clearly suggest that if the needles are a lot moister, that's going to slow down our rate of spread. And so that's done just using this foliar moisture effect equation, where we plug in the foliar moisture content, solve it, and it'll give us this effect, which we'll see is just going to be another modifier on our final rate of spread. So the way this works is the foliar moisture effect that we use is really a ratio between some condition, whatever condition we're predicting for, and a normal value, or essentially the value that was used in building 91. The issue is they didn't measure foliar moisture content on those fires. At least for the crown moisture content, there's some estimates for maybe the live fuels on the surface, but we don't have a great estimate for the actual foliar moisture contents in the crowns. So we're just going to assume a mean value of 100% across all those fires to set as our standard, and then basically the final equation is the foliar moisture content, or sorry, the foliar moisture effect for whatever your measured foliar moisture content is, divided by the normal foliar moisture effect, which would be the foliar moisture effect for 100% moisture. All right, so if we assume that at the time of those fires measured by Rothermel, our range might have been 85 to 120, and we basically assume that they would average out to 100% to set as our baseline foliar moisture effect. And when we plug it into that original foliar moisture equation, we come out with this fairly small number. So this extension, right there, there's some assumptions related to Van Wagner's foliar moisture effect equation, not really empirically tested, and then also just the underlying assumptions of Rothermel 91. This tends to not have, 100% is used a lot of the time just because we often don't have these foliar moisture content measurements. But yeah, there's also all these kind of underlying assumptions to this extension here. So a big goal in the fire modeling community, right, has been to put together a fire model that can simulate the full range of potential fire behavior using just one model. If we're going to do one model, we really need to look towards a truly physical model that's going to be able to capture all those dynamics in one, or a system of models. And that's kind of what we've been looking at, where we're linking together all these models for different components of the potential fire behavior sort of spectrum, and then linking them together so that we can make predictions about surface fire spread, and then how that fire might initiate into the crowns, and then ultimately spread through the crowns. So the system we've been looking at links all of these different models together, right? We looked to Rothermel in 1972 to predict our surface fire rate of spread. We've got crown fire from Rothermel 91, so that's rate of spread, and then we have initiation from Van Wagner. We have that criteria for basically the minimum spread rate to sustain active crown fire from 77. We're using surface fire and reaction intensity sort of interchangeably from Byram in 59, and as well as it was defined in Rothermel 72. So here's what that looks like when we link these models together. Right, so kind of working step by step down from the top. Right, if we want to make a prediction about any given stand, the first two steps really are to make a surface rate of spread prediction from Rothermel, and then simultaneously we'll make an estimate of the critical surface fire intensity, right, required for crown ignition. So if the reaction intensity predicted by Rothermel is less than the critical torching or critical crown fire initiation intensity, surface fire would be predicted to occur, and we can just go ahead and use our estimates of flame length and rate of spread and everything else that comes out of Rothermel or whatever modeling software you're actually using. But if the surface fire reaction intensity is greater than the critical ignition intensity, then crown fire initiation would be predicted to occur. And now we need to make another determination of whether active crown fire is going to be possible. As we saw, this actually has a few different components to it. Right, so first maybe we need to estimate our critical rate of spread. So what is the minimum spread rate needed for active crown fire propagation? And then we need to make a prediction of the crown fire rate of spread. So that would be in Rothermel 91. But to do that prediction, we're going to need to make an additional surface fire prediction based on fuel model 10 with a wind adjustment a factor of 4. So that's actually going to be separate from the actual prediction we make up here at the top, right, for our original surface fire rate of spread prediction, because that prediction would be for whatever surface fuel model we actually, are trying to, we think represents our stand. But no matter what we use up there, when determining crown fire rate of spread, we're using this fuel model 10 because that was what Rothermel used to create his correlation. So anyway, we go ahead and we make that additional surface fire rate of spread prediction. We multiply it by 3.34, and that gives us our estimate of the active crown fire rate of spread. We compare that to the critical rate of spread from Van Wagner, and we can determine if it's going to be passive crown fire, right? So if that R10 rate of spread is too slow, then active crown fire isn't going to be sustainable, and we're just going to have more passive behavior where trees and individuals are torching, but spread rate's a little bit slower. But if that R10 prediction is greater than our critical rate of spread, well, now we have active crown fire, whose spread rate's going to be, R10 times 3.4 times the foliar moisture adjustment if we're using that. So that's sort of the framework of how we're linking all this stuff together. So when we link all this stuff together, right, we can get an estimate of the type of fire. We get estimates of the spread rate and intensity for both surface fires and fully developed crown fires. But at least in its current setup, we're not exactly sure what to do about passive crown fire. We've made some predictions that might occur, but what rate and spread intensity are going to occur during a passive crown fire? So there's some different ways to go about doing it, and we're going to look at how this works in Behave. So Behave gives us two options really for dealing with this sort of intermediate range of crown fire behavior, or the passive crown fire. So in method 1, really the default method in Behave 6 is that if the fire type is predicted to be surface or passive crown fire, you're just going to use the rate of spread for a surface fire. So the assumption there is that that passive crown fire behavior is going to be contributing to intensity, right, as those canopy fuels burn, but the tree torching isn't really contributing to the forward rate of spread for the fire. So basically, the assumption there is that it's unchanged versus it just being a surface fire. And then if the fire is determined to be active, then we'll use the Rothermel 91 equation. And then there's also the second method based on some ideas outlined in Scott and Reinhardt's 2001 paper. And basically the idea is that when we have passive crown fire, there's a whole range of potential behaviors there, right? Passive crown fire could be 1 out of 10 trees torch up, or it could be that 95% of the trees are torching. It's just happening sort of in tandem with the surface fire, and it's not really spreading independently or actively. Right, so the idea here is that there's maybe some range of behavior where if 1 out of 10 trees is torching, then we probably want to use our surface fire rate of spread. But once we're talking about a really large portion of that stand torching, we might expect it to have a faster rate of spread, right? A rate of spread that's going to be pretty close to our active spread. So in that Scott and Reinhardt method of calculating the final rate of spread for a passive crown fire, they use some stuff from Van Wagner's 89 and 93 papers, where basically what we're going to do is estimate our surface fire rate of spread, and then we're going to estimate basically compare the active rate of spread to that surface fire rate of spread, how far apart are those two things, and then multiply that by the fraction of the crowns that are burned. So basically it's just fitting this linear equation between surface fire rate of spread and active rate of spread as you burn more and more of the crowns. So in Van Wagner 93, he gives us this method to estimate the crown fraction burned, which is basically this equation here, where we have basically the difference between the predicted and critical rates of crown fire spread. So basically, how close is our predicted spread to the actual critical value necessary for active spread. And if we have fully active crown fire, right, we don't need this equation anymore. We're kind of assuming 100% consumption or close to it. And then there's this additional scaling factor built in there, once again kind of based on this comparison of the active rate of spread and the rate of spread for the initiation of active crown fire. Right, and so we plug all that stuff together into this equation here that's used in the ultimately used in the Scott and Reinhardt method. And then we just have this figure here that maybe makes this a little bit clearer, where we have basically our open wind speed on the bottom, right? So as we increase the open wind speed, our predicted spread rates are all going to increase. And so you can see if we follow that, the dotted black line along the bottom there, eventually the rate of spread there is going to get up high enough that we're going to reach our initiation requirement, and we're going to enter that passive crown fire zone. And then once we're in the passive crown fire zone, there's this linear increase in the predicted spread rate as our crown fraction burn increases, until that till we hit that our active line, right, until our spread rate's fast enough to sustain active crown fire, and then we shift into the active crown fire mode, where we go back to using the Rothermel 91 correlation. So that's how we can calculate rate of spread using some very different methods, and we can also adjust our final fire line intensity using a similar method where we're basically adding the heat release per unit area of the surface fire to basically the heat release for the canopy fire, which we find by calculating the weight of the canopy times the height of the canopy and the crown fraction burned to give us a total mass consumed, and then we multiply that by our rate of spread, and so this is similar to the Byram's method, right? It's just lumping the surface and the crowns all together to give us a final intensity. And then about our crown fire flame length. So in Behave, the surface fire flame lengths are estimated using a correlation from Byram 59, which is right here. Right, it's just the intensity raised to the scaling factor times another constant, and that gives us the blue line there on the right. But it was pretty clearly observed that this equation, seems to work fairly well in surface fuel complexes, but it was majorly under predicting flame lengths in crown fires. So once we've stepped into the active crown fire mode, Behave is going to use this equation from Thomas 63 that just predicts some longer flame lengths and does a better job dealing with flame lengths out of this really tall, very porous fuel bed. If you think about the entire forest as your fuel bed, right, the crown component is a lot more open and porous, and so we get much larger flame lengths out of there than for the more compacted surface fuels. All right, so yeah, this process of linking together these models is used pretty similarly across a range of different fire modeling software, right? So we've seen this is the approach taken in Behave, and then very similar linkages are used in Nexus, the FFE extension for FVS, and then Farsight and FlamMap. Right, so they all kind of connect these individual models together to try and capture, right, a full range of fire dynamics. But when you do all these linkages, right, you're basically just kind of stacking assumptions and limitations as you go, right? Because you kind of absorb all of the assumptions made by your various underlying models, and so we end up with this list, which is probably even still incomplete, but some of our big assumptions here, right? We are making this assumption that fuel weather and topography are all homogeneous within the fuel cell, or really across the area for which we're making our prediction. Our surface fire rate of spread is this quasi steady state rate of spread for a head fire, as we've discussed, or maybe the rate of spread for just a wind dominated crown fire, but so there's some limitations in there. We're not accounting for any of the impacts of the convective flow on wind speed. So, as we've discussed, fires can generate their own weather at both fine or small and large scales, where the actual convection coming off of our fire line is going to have a pretty strong effect on wind speeds. So none of those dynamics are captured in these models. We're limited by experiments at basically every step of the way. We needed to keep in mind all these different empirical constants derived by Rothermel and Van Wagner. Some of our estimates about or discussions about how wind adjustment factors are calculated and how we might select them based on what our vegetation looks like. This assumption that winds are steady state spatially and temporally, And then we also, our big linkage between surface and crown fire is based on IR, or the reaction intensity from Rothermel, which we assume is the same or can be used in exchange for reaction intensity or fire line intensity, really, from Byram.